Alright guys, today we are talking about rational functions. So first of all, let's give them a formal definition. A rational function is a function that can be written in the form f of x equals p of x over d of x, where p of x and d of x are polynomials. So basically, a rational function is just a function that looks like a fraction. We've seen these before. They look like, say, something like this. When have we looked at these before? When have we seen functions like this in the past? We've seen them when we're looking for domain, right? When we were practicing finding domain symbolically. So let's refresh on that. Let's find the domain of this guy. Well, remember our two domain rules that we have are we need to look out for even roots and also for denominators. Polynomials don't have roots, so we should not have to worry about that. But we do have a denominator here. What do we need to look out for with the denominator? We need to make sure it's not equal to 0, right? So the way we did that was take the denominator and set it not equal to 0, right? Because we wanted to figure out where is this not 0. We solve, in order to solve a quadratic, we need to factor. So this one is going to factor into x minus 5 and x plus 3, right? Because negative 5 times 3 is negative 15, and negative 5 plus 3 is negative 2. Then we can set them each individually not equal to 0, right? We split it up like this because whenever one of these factors is not 0, right? Because in order for this to not be 0, we need both of these factors to not be 0. So we know that x is not 5. We know that x is also not negative 3. So our domain is all real numbers except for those two guys. So we have negative infinity up to negative 3, union negative 3 to 5, union 5 to infinity. If that was difficult for you to see, maybe it might be helpful for you to draw it on a number line, right? We have got negative 3 and 5, and we want both of those to be open, and everything else is included. So that's what we get there. That's the domain of a rational function. It's everything except for the roots of the denominator. Let's look at another one super quickly. Let's say we've got something like this. Find the domain. Okay, again, remember we're looking for the roots of the denominator. That means we want this whole guy to be not equal to 0, which means that each of these factors we need to set individually not equal to 0. And we end up getting that x cannot be 1, -3, or 4. That's a bunch of stuff. let's draw our number line again super quickly just to make sure we get everything totally in the right place. So our lowest root is -3, then we have 1 in the middle and 4. We want each of those to be open, right? Because x cannot be any of those. And then everything else is included. So we've got -∞ to -3, -3 to 1, 1 to 4, and 4 to infinity. So if we're looking back at this original question, something that you might have thought at first when we were first looking at it is, well, hey, so I've got this factor on top of x minus 1 and underneath as well, right? Same thing with this x plus 3. Does that mean that I can cancel those and then I don't have to worry about it? No, so we still have, even though, normally if we had like a 2 and a 2 in the numerator and a 2 in the denominator, or like a -27 in the numerator and denominator, a factor of something like that, right, just a regular constant, we could definitely cancel those out, right, because multiplying by something and dividing by it sort of kind of undo each other. But whenever we have something that involves x, we have to make sure that we use our domain rules before we simplify, right? That's super, super important. We've been doing that since the beginning, right? Whenever we talked about the domain of compositions of functions or combinations of functions, we always had to take the domain before we did any simplification. And the same thing is true here. So even though we might cancel repeated factors, we always need to exclude all roots of d of x, right? And what is d of x? Well, if you'll recall in our definition, we said that a rational function looks like p of x over d of x. P of x, the way I like to remember it, is like a polynomial on top, and d of x is like the denominator, which is, also known as, aka, where d of x equals 0. So even though, right, we do have the same factors here, we still needed to look at what our roots were of the denominator, right, and exclude those from the domain. So why did we exclude those from the domain? Well, let's recall sort of our visual representation of what we've been doing here. Let's do that by looking at our simplest rational function. So remember that our graph for something like 1 over x has this shape. Right, where we had this vertical asymptote here, right, where we got really, really close but didn't touch, both here and here, right? So we had a vertical asymptote at x equals 0. That was because we had that factor in the denominator, right? So what's going on with one of these examples? Let's look at this first example really quickly. If I graph this in Desmos, I can see that that -3 and that 5 both correspond to vertical asymptotes, right? And those values are being excluded from our domain because there's no value of the function there. So when we have a factor underneath that is not also on top, means we have a vertical asymptote. Now, if we look at this second example, it gets a little bit tricky when we're dealing with these roots, right? 1 and -3. There's something else going on. We clearly don't have a vertical asymptote there, but there's something going on because we're removed from the domain. We can see that we do have a vertical asymptote at 4. So when the factor is on its own in the denominator, that's going to give us a vertical asymptote. But when we have these repeated factors, it's going to be something else. So let's write that down really quickly. So let's write that down somewhere. A root of the denominator that is not also a root of the numerator is the value of a vertical asymptote. Since it's in the denominator, this x value is removed from the domain. Awesome. Okay, so what the heck is going on with those other points? So what's going on when we have those repeated factors? Let's look back at this example from before. So we do know that it's going to give us something that will need to be excluded from our domain. If we look at those points, we have open points at -3 and at 1. So what does that mean? Well, open points mean that our function is not defined at that point. That hole occurs right on the graph in line with the rest of the graph, right? So it kind of looks like we just took a little bite out of the graph. So why is that happening? Well, if we look at let's look at a graph. I'm going to copy this function down at the next part of our notes. So again, this is the same thing from before. We've got 2, x minus 1, x plus 3 over x minus 1, x plus 3, x minus 4. So I would like for us, just for a second, to see what would happen if we sort of simplified this function. In order to simplify this, I'm going to write this as g with a small s for simplified. If we simplified this, right, and got rid of these repeated factors, since they're in the numerator and the denominator, I would be left with, well, 2 is still there. X minus 1 is canceled. X plus 3 is canceled. So 2 over x minus 4. Just out of curiosity, let's graph this as well. When I graph this graph, I get something that looks just like g of x without the hole. Holes. So what do we notice about where the holes are occurring? Well, we said we were looking at the x values, right? 1 and -3, the roots of the denominator. So we had x equals repeated roots. We had x equals 1 and x equals -3. If we know that this function looks just like this graph without the holes, then we can find the y values of where these are going to occur by plugging into this guy, right? So what is g sub s of x at these x values? So g sub s of 1 gives me 2 over 1 minus 4. So that's 2 over -3. And what is g sub s of -3? Well, looks like I've got 2 over -3 minus 4, which gives me -7. If I look at these points, looks like I'm getting 1 and then -0.6667, right? 666 repeating. And this guy is going to give me -3 and -2 over 7, so -0.286. And what do we notice about these points? Well, these are exactly where those open points were on g of x, right? These are the open points and we are going to call these holes. The holes. Holes occur, let's write this down as well. Holes occur at the root given by a factor that is both a factor of p of x, the numerator, and d of x, the denominator. The y value of the whole can be found by plugging the root into what we'll call f sub s of x, the rational function with the repeated factors removed. So what we're saying is that we will simplify the function and plug that root in to the simplified version of the function to find the y value. So let's give this a shot. Let's say that we have something like f of x equals 3 times x minus 5 times x plus 1 over x plus 2, x minus 5. So find the coordinate pair of a whole. So, all right, what do we know? Well, we know that the x value, right, the Yeah, the x value of the whole is going to come from a repeated factor. That repeated factor is clearly this x minus 5 and x minus 5. So x minus 5 equals 0. We get x equals 5. This is the x value of the whole. Now, again, we know that the graph of this function doesn't matter what it looks like, but we do know that it's going to look like whatever's left over when we cancel these guys, right? So let's write that new function. F sub s of x equals 3. We're going to cancel x minus 5, so we have x plus 1 over x plus 2. Now we can plug this value of 5, this x value, into this function. F sub s of 5 gives us 3 times 5 plus 1 over 5 plus 2. So 3 times 6 gives us 18 over 5 plus 2 gives us 7. So we have a whole at the point 5 and then 18 over 7. If we plug 18 over 7 into a calculator, we end up getting about 2.571. If we look at the graph of this really quickly, we can see that we have a hole at that point. Okay, what else can we see from a rational function? Well, let's go back to visit that original. Let's look at that original f of x that we were talking about, the first example we looked at today. So x minus 3 over x squared minus 2x minus 15. What are some other important features of graphs that we've talked about so far this semester? Well, we've definitely talked a bunch about intercepts, right? Aren't those kind of easy to find and fairly important part of a graph? Yeah, so let's go ahead and see if we can find those. So remember, an X-intercept is going to look like what? What is the form of an X-intercept? Let's say we want it in coordinate point form. Well, remember, it's where we intersect the x-axis. The x-axis is the line y equals 0, so all of the points along that line are going to have y equals 0. And then it's some x value, right? Similarly, with the y-intercept, that's all of the points where x equals 0, and we have some y value. Okay, so for each of these, let's go ahead and think about how we can find these mathematically. Well, right, if we know that y is 0, then, and we're looking for x, then can't we replace the output, right? 0 is our output, right? Y is our output, right? Y typically represents our output. F of x is the output of our function, so we can replace f of x with 0, right? This is just where is f of x equal to 0. Similarly with the y-intercept, right? Again, this is where x equals 0. So we can just look for f of 0, right? Replacing x with 0. So what happens when we do this here? So if we're looking for where f of x equals 0, I can start with 0 equals x minus 3 over our denominator. With a fraction, what do we know about when a fraction is equal to 0? Well, a fraction is equal to 0 when the top is equal to 0, right? Because 0 divided by anything is equal to 0. So we really just need to look at where the numerator is 0. The only caveat to that is that we need to make sure that whatever gives us 0 on the top doesn't also give us 0 on the bottom. So we've actually already found what gives us 0 on the bottom, right? From our earlier example, we got that x cannot be 5 because that gives us 0, and we found that x cannot be -3. What is the root on top? What makes the top equal to 0? Well, we can figure that out by looking at x minus 3 equals 0 when x equals +3. +3 is not -3 or 5. So this will give us 0 on top, right? Which means that we'll get 0 over, whatever it is when we plug in 3, which is not 0. As long as it's not 0, then the whole function is 0. So x equals 3 is our x-intercept. So we have an x-intercept at 3, 0. Right, so let's write that down really quickly. That we got this from because it was a root of the numerator. So a root of the numerator, p of x, that is not a root of the denominator, is the x value of an x-intercept. Right, and then we know that the y value will, of course, be 0, right? That's how x-intercepts work. Now, moving on to the y-intercept, I'll split this up with a line. Again, we said we wanted to find f of 0. That's much more simple than this. F of 0 just means we plug in 0 everywhere we see x. So we've got 0 minus 3 over 0 squared minus 2 times 0 minus 15. That gives us -3 over 0, 0, -15. These negatives are going to sort of undo each other, right? So it's going to be positive. Then we've got 3 over 15, which reduces to 1/5. So we have a y-intercept of 0, 1/5. That was super easy, right? The y-intercept of any function, actually, not just a rational function, f of x can be found by computing f of 0. Easy enough. All right, so we've talked about vertical asymptotes so far, right? Those were, again, the roots of the denominator that weren't also roots of the numerator, right? Because if it was both, then it would be a whole. Horizontal asymptotes, we're going to have to use a very, very different method to find. In order to introduce horizontal asymptotes, I'm going to start us off with a fact that's going to seem maybe a little bit irrelevant. The end behavior of a rational function f of x equals p of x over d of x will be the same as that of the quotient of p of x over d of x. Okay, so quotient of p of x over d of x. Let's look at a couple of examples here of what that might look like. So the first example I would like to look at is this function f of x equals 3x squared plus 2x plus 2 over x squared plus 5x plus 1. So first of all, what does this function look like? Let's look at it. So I'm going to graph it in the notes here so we can see what we're looking at. So we have it kind of copied down. Looks like we've got this sort of vertical asymptote. I'm looking at this in Desmos. We've got this vertical asymptote, and then we've got a horizontal asymptote here. That's what we're, trying to find right now. The graph looks like this in this upper portion. Then we've got this like funky looking part that's down here. And then we've got this crazy thing that kind of swoops down and then comes back up and gets really, really close to that line. This line is y equals 3. So first of all, I'd like for us to determine the end behavior of this graph just from looking at it. So what is the end behavior here? Remember, that looks like this, right? So as x approaches negative infinity, f of x approaches what? And as x approaches positive infinity, f of x approaches what? So for negative infinity, right, that's asking where are the y values of the graph going as we move off the graph to the left, as x moves towards negative infinity. That is this y value, right, which is 3, right? So f of x is 3. Similarly, as we move off the graph to the right, as x moves to positive infinity, as x is getting really large, f of x, or the y values, are getting really, really close to 3 as well. So that's pretty typical of a function that has a horizontal asymptote at 3, right? We have a horizontal asymptote at y equals 3. Again, with asymptotes, of course, they're lines, so we always want to write it as an equation, and when it's horizontal, it's y equals. So we have y equals 3, but let's think about what our fact tells us. So it said that our end behavior, right, is going to look like the same end behavior as the quotient of p of x over d of x. So let's find the quotient, right? That means we need to divide this numerator by the denominator. So let's set that up really quickly. We've got x squared plus 5x plus 1. We have to do long division because we have a quadratic in the denominator. Our numerator is 3x squared plus 2x plus 2. We divide first term by first term. That's 3x squared divided by x squared. We're left with 3. 3 needs to go above the constant term, so that's right there. Now, that's the constant term. We've made it to the end of all of our digits, so this is actually all our quotient is, right? We could do the whole like multiply by the divisor and whatever, and that would give us the remainder, but we're not asked for the remainder. We're just asked for the quotient. So the quotient is 3. The line, y equals 3, of course gives us the same end behavior as this graph because, well, y equals 3 was the horizontal asymptote. So of course they have the same end behavior. So we can find the horizontal asymptote by doing this division. And it didn't take very long, right? Because we had the same number. Super easy. Didn't take very long because we only had to find this guy. Let's do another one. Let's say we're looking at g of x equals x over 2x squared plus 1. What does this function look like? Well, definitely looks like, again, I'll graph it here. We've got this guy that kind of dips down and comes through and dips down again, just like that. We're clearly getting very, very close to the x-axis, which is the line y equals 0. So we have a horizontal asymptote. At y equals 0, based on the graph. Let's use our quotient rules here. So to set this up, we write out our long division. We've got 2x squared plus 0x plus 1 dividing x plus 0, right? We definitely want to make sure we have those placeholders. Now, I divide first term by first term. Can I do this? Can I divide x by 2x squared? I can't, right? I'm going to draw a big X, not to be confused with the variable itself. Nice and clear that we're not talking about the variable x. So we can't do that, right? So how many times can this fit into x? 0 times, right? 2x squared is way too big to fit into x. So our quotient here is 0. So this tells us that we have a y-intercept of y equals 0. Let's try one of these as an example without the graph. So let's say we have f of x equals negative 2x squared plus 2x plus 23 over x squared minus x minus 10. So let's use our fact to figure out the horizontal asymptote here. Well, again, we're dividing, so we have x squared minus x minus 10 divided by negative 2x squared plus 2x plus 23. I divide first term by first term, so that's negative 2x squared divided by x squared. I can cancel the x squareds because we have it on top and underneath. And we're left with negative 2. That goes right above the constant term 23, and that means that we have a horizontal asymptote of y equals negative 2. Let's say we have g of x equals x plus 2 over 2x cubed plus 3x plus 1. Let's set up that division problem. So we're dividing by 2x cubed plus 0x squared, right? Can't forget that placeholder, plus 3x plus 1, and we're dividing x plus 2. Again, our first term, we're dividing first term by first term. So we have x over 2x cubed. Can I divide x by 2x cubed? Definitely not, right? We can't fit 2x cubed into just x, so this is 0. Which tells us, again, we can't do this And again, I will mark it with a color so we don't confuse it for a really big X. This tells us that y equals 0 is a horizontal asymptote for this function. Do we notice a pattern here? So I want to look back at our first function that we looked at, which was this guy, right? We had 3x squared and x squared. When we did this division, we got 3, right? So some non-zero number, something that wasn't 0. And we had a horizontal asymptote for that. If I think about it, why did I get 3? Well, I got it because I divided the first term by the first term, and it gave me 3, right? Because they had the same degree, right? We were dividing something with the same degree, the x squared by the x squared. And the same thing happened with this one, right? We got -2 because we were dividing x squared by x squared. Those canceled, we got -2, and that was my quotient, which gave me this horizontal asymptote. What does this tell us? Well, this tells us that the number that we can think about this in terms of, well, if we're looking at the number we got here, if this is the value of our horizontal asymptote, it's going to be the leading coefficient over the top over the leading coefficient of the bottom. So if p of x and d of x have the same degree, f of x has a horizontal asymptote at y equals the leading coefficient of p of x over the leading coefficient of d of x. Simple as that. We can really easily figure it out by doing this whole division thing, or we can sort of think about it in this way. Similarly, with this part, right, this second example, which was very similar to the one that we had up top of this page, right, this guy, what do we have in common here? Well, we have a degree on top that's smaller than the degree of the bottom. And that was what caused us to get an answer of 0, right? Because we couldn't fit that larger degree into that smaller degree. So if the degree of p of x is smaller than the degree of d of x, then f of x has a horizontal asymptote at y equals 0, right? Both cases gave us 0 for the quotient, so our end behavior approaches 0. Okay, so we've looked at the case where we have the same degree. We've looked at the case where we have a smaller degree in the numerator, right, on top. But we haven't looked at the case where we have a larger degree on top. So let's look at an example of that. So let's say we're given something like this. H of x equals 2x squared minus x minus 10 over 2x minus 5. Sorry, plus 5. So let's try our division trick here. We're dividing by 2x plus 5. Our numerator is 2x squared minus x minus 10. We divide first term by first term, so that's 2x squared divided by 2x. That gives us, the 2's are going to cancel. One of these x's is going to cancel, so we're left with just x. So we have x. We want to multiply that x by our divisor. We get 2x squared plus 5x. So we have minus this. This is going to be 0. Negative x minus 5x is negative 6x. We can bring down this negative 10. Again, we divide first term by first term, so we have negative 6x divided by 2x. The x's are going to cancel. We end up with negative 6 over 2, which is just negative 3. That's going to go directly above our constant, negative 10, so we have negative 3 up here. So this time we have a quotient of x minus 3. We're done at this point, right? We could continue and find the remainder, but it's not important to us in this context. We got y equals x minus 3 here. So our rule, our fact that we talked about, tells us that our end behavior is going to look like this quotient, right? So our end behavior is going to look like x minus 3. So let's look at the graph of this really quickly. So I am again taking this from Desmos. I'm going to graph this one because we haven't looked at one of these yet with the graph. First of all, I'm actually going to graph this line first. So y equals x minus 3. That's just a line, right, with a slope of 1 with a y-intercept of negative 3. So looks like this. The graph of this function is actually going to look like this. It's going to swoop down and then come back up and get really, really close to this line, but never quite touch it. Whoops. And similarly down here, we get really, really close to this line and don't touch it, and then we kind of come down. And actually, we have a vertical asymptote here. So the end behavior of this function, right, the function is getting really, really close to x minus 3 on both ends. What can we say about this? So this is actually called, this line, y equals x minus 3, is what we're going to call a slant asymptote. Let's do a quick definition of that in our notes. An asymptote that is neither horizontal nor vertical is called a slant asymptote. So, right, that one that we just looked at was a line that was not horizontal or vertical, so it was a slant asymptote. And where did it come from? Well, again, let's look back at this guy. So similarly to before, we've been talking kind of about how the degrees of the functions are affecting what we're talking about. So the degree of the top was 1 degree higher than the degree of the bottom. Because it was 1 degree higher than the degree of the bottom, the first term that we got was x, right? Anything with x in it, just plain x, maybe it's 2x or maybe it's 3x or negative 5x, but it's not x squared or x cubed or whatever. Anything with x is a line. So we have this line that looks like the end behavior of our graph. So slant asymptotes, where we have a line, are going to occur when we have a degree of 1 larger on the top than on the bottom. So slant asymptotes occur when the degree of p of x is exactly 1 larger than the degree of d of x. Before you ask, it's possible for us to have quotients when we divide the numerator and denominator of a rational function. It's possible for us to have something that has a higher degree than a line, so like an x squared or an x cubed, but we're not going to see them in this class. So we are just talking about slant asymptotes here. One thing I would like for us to notice is that, remember, we found all of these by finding the quotient of the function, right? There's not going to be more than one quotient of the function, or we're not going to get two different quotients, or we're not going to, we're never going to get two different, it's never going to give us two answers. So in our quotient, when we do that division, we can either get something that is linear, right? That looks like a line, or something that looks like a constant, right? We can't get both. So we can't have a horizontal asymptote and also a slant asymptote. We can only have one. So we cannot have a horizontal asymptote and a slant asymptote. For one function. Right? Either, as we move off the sides of the graph, the function is approaching something that's a slanted line, or it's approaching a given value, right? A perfectly horizontal line. It can't be approaching both. So we can only have one, and it will be whatever you get when you do that quotient. Okay, I'd like to look at one example from the lab manual really quickly. This is in the Rational Functions Part 1 section. It's asking us to find the domain for A, vertical asymptote for B, horizontal asymptote for C, zeros or x-intercepts for D, coordinate of the whole for E, and y-intercept for F. So let's go ahead and do that. So our A is our domain. For that, in order to find domain, we did the normal stuff, right? We took the roots of the denominator and set it equal to 0. That would give us x equals 4 from this factor and x equals -3 for this factor. We don't want those values to be included in our domain, so we exclude them. That would give us -∞ to -3, -3 to 4, and 4 to infinity. Part B is our vertical asymptotes. Remember, we found those by looking for the roots of the denominator that were not also roots of the numerator. We have one root of 4 underneath, right? That is not repeated on top. We do have a vertical asymptote at x equals 4. Again, we always want to write it with x equals for vertical asymptotes. That's very important. Or, whatever our input value is, because we are writing the equation of a line, so it needs to have an equal sign. Do we have a vertical asymptote at x equals -3 as well? Well, let's look. Do we have -3 as a root for the numerator too? We do. So what does that mean? It means that we don't have a vertical asymptote because we have a hole, right? If it's repeated, we have a hole. So we do have a hole at the x value, x equals -3. I'm going to write that under E, where it asks us to find the coordinates of a hole. And that means that x equals 4 is our only vertical asymptote. Let's go ahead and find the hole because we're sort of started with that process here. We want to simplify, right? We need to find f sub s. F sub s, again, is when we sort of get rid of our repeated factors. So that's x plus 3. So if we look at f sub s of x, we're just left with x over x minus 4. If we plug in -3 to f sub s of -3, that's just -3 over -3 minus 4 is -7. So 3/7. So we have a whole at -3 and 3/7. That's it. Okay, let's go back to C. C is the horizontal asymptote. In order to find the horizontal asymptote, we need to think about our rules that we had. We had that rule with the quotients. So we could either do that division, which would require us to do all the distributing, right? We'd have to distribute x here and FOIL here, so we had them in standard form. Instead of doing that, let's just think about those rules, right? The rule that we used depended on the degree of the numerator and the denominator. The degree of the numerator is x squared, and the degree is 2, right? We have 2 roots. The degree of the denominator is 2, because we have 2 roots here as well. So we have the same degree on the top as on the bottom. When that happened, when we tried to do that division, right, we would have those first terms when we divided the first term of the numerator by the first term of the denominator. When we divide the first term of the numerator by the first term of the denominator, we end up just getting x squared over x squared, which is just 1, right? The leading coefficient over the leading coefficient. So when we have the same degree in the top as on the bottom, then our horizontal asymptote is just the leading coefficient divided by the leading coefficient. Here we have 1 over 1, which is just 1. D is the zeros and the D is the zeros or x-intercepts. Remember, that was the root of the top, right? Because the x-intercept is where the output of our function is 0. In order for a fraction to be 0, we need the top to be 0, right? But not the bottom. So there are 2 roots of the top. One is x equals 0 from this factor of x, and one is x equals -3 from this factor of x plus 3. So x minus 3 is both a root of the top and the bottom, so we know that that gives us a whole, so that's not going to give us an x-intercept. But x equals 0 is. So we do have an x-intercept of 0, 0. What about a y-intercept? Well, y-intercept again was f of 0. So we can calculate this by looking for f of 0. We plug in 0 for all of the x values. We have 0 on top, 0 plus 3, 0 minus 4, 0 plus 3. We end up with 0 times 3 over -4 times 3. And of course, 0 times anything is 0, and then 0 divided by anything is also 0. So we have a y-intercept of 0, 0, which we could have potentially figured out from here, right? Because this is a point with x equals 0, right? Y-intercept has x equals 0. So we've got 0, 0 for both our x-intercept and our y-intercept. I'm going to circle all of the answers here. At the end of the day, we have y equals 1, x equals 4, and this whole thing is our denominator. Okay, so long lesson, lots to learn, but we are going to practice this all week and get used to all of this stuff. So hopefully you're not feeling terribly intimidated by it. We're going to get tons of practice. Don't worry. All right, guys, thanks for sticking with it, and I'll see you next time.